Assalamu alaikum, I am Ashaful Islam, my ID 1095. Our presentation topic is pegging in operating system. Now I am talking about introduction to pegging. The concept. Pegging is a memory management scheme that eliminates the need for contiguous allocation of physical memory. It allows a process's physical addresses space to be non-contiguous. The problem solved. It specially solved the problem of external fragmentation that plugs contiguous memory allocation method, ensuring efficient use of RAM. K terminology. Logical. Logical memory is divided into fixed-sized blocks called pages, numbered 0, 1, 2 and continues to n. Physical. Actual location in RAM physical memory is divided into fixed-sized block called frames. Crucial, frame size must equal page size. Now I am talking about mapping process. Logical versus physical. The operating system maintains a page table for each process. This table serves as the map looking the pages the program sees to the actual frames in memory, visualizing the split between user view and hardware reality. Now I am talking about address translation. Logical address generated by CPU divided into pages equal to P and D. P equal to page number, D equal to page offset. Physical address calculated by hardware address equal to P and D. F equal to frame number, D equal to offset. Hardware implementation. The memory management unit handles the translation at runtime. Extract page number P, look up frame F in page table, combine F with offset D. Address physical memory.
Assalamu alaikum, very good morning to all. This is Nafisa Tasnim Isha, last 4 digit of my ID 1084. My presentation topic is paging. I will talk about paging. I will explain the how computer find, manage and protect memory. Let's first of all we talk about the addressing translation. The CPU use a logical address which has a page number, but the main memory or RAM use a physical address, so the system must change the logical address into a physical address to find the data. Hardware implementation. How does it work? It is done by hardware called the MMU. The MMU use a page table. Think the table use a like a map. It connect the CPU page to the correct page in the memory. Hardware acceleration. But there is a problem. Checking the table in RAM is slow. It makes it fast. When we use the special cache table TLB, the TLB save reset address. If the address is in the TLB, CPU get it fastly. This makes the computer very fast. And memory protection. Paging also keep memory saving. We use special protection bit. For example, a valid unvalid bit. Check if the program is allowed to access the memory. They stop the program and or other it's crash the computer. And share page. Finally, share pages to solve the specific different program can be shared the same code like library. They share the code, but they keep their own data in separate. This is very efficient. To sum up, paging makes memory management fast, safe and smart. That's all of my part. Thank you for the listening.
Alaikum, this is Mahmoud Hassan. The last 4 digit of my ID is 1093. I'm talking about hardware acceleration, TLB and effective access time. Here you can see the formula for effective access time or EAT. The symbol alpha represents the hit ratio, which is how often the processor finds the desired page directly in the TLB. If the hit ratio is high, like above 90%, our memory access time decreases significantly, making the system faster. However, if a miss occurs, the system has to access the RAM, which takes twice as much time. Therefore, the performance of the TLB relies heavily on the hit ratio. Now I'm talking about hierarchical paging or multi-level paging. Now the question arises, what happens if our memory space is very large? Modern computers often use 32-bit or 64-bit logical address space. As a result, the page table becomes messy, making it different to store it continuously in a main memory. To solve this problem, we use hierarchical paging or multi-level paging. Simply put, we break the page table itself down into smaller pages. You can think of this concept like a large book's index. If the index is too large, you might need a separate index, just a negative in main index. Now I'm talking about hashed page tables. When the address space exists 32 bits, standard paging becomes inefficient. In such scenarios, we used hashed page tables. In this method, the virtual page number is mapped to a hash table using a hash function. A common issue there is collusion, where multi-level page numbers produce the small hash value. As you can see in the table, as you can see in the side, we handle collusions using a linked list. That means pages with the same hash value are changed together for rational. Now I'm talking about invert page table. The methods we discussed so far require a specific or separate page table for every single process, which consumes a significant amount of memory. To save memory, we use the invert page table. This works in the opposite way of standard paging. That's all for today. Thank you.
Assalamu alaikum. Myself Sadrul Amin. My ID last 4 digit is 1322. Today's presentation topic is paging versus segmentation. In this slide, we compare paging and segmentation. Paging divides memory into fixed size blocks, which is efficient and eliminates external fragmentation. Segmentation divided memory based on logical unit like fraction or array, so segment size vary. In modern system, paging is most preferred because it is similar for memory management, allow protection at page level and avoid large gaps of unusual memory. Demand paging. Now let's talk about demand paging. Normally programs are loaded fully into memory before execution, but demand paging changes its approach. Instead of loading everything, only the pages that are actually used get loaded into RAM. This improves performance because unnecessary pages are kept on the disk. Demand paging allows application to start faster, reduce memory waste, and help the operating system run many programs even when RAM is limited. Because of this, system today support large programs without having all memory available at once. Page fault. Here we see what happens during a page fault. A page fault occurs when a program tries to access a page that is not currently in RAM. When that happens, the CPU traps to the operating system. The OS then checks whether the page is valid. If valid, it found a free frame and loaded that page from disk into memory. After that, the page table is updated, the page becomes valid, and the instruction is restored. This ensures seamless execution even when data is not immediately available. Conclusion. To conclude, paging is the foundation of modern operating system. It enables efficient memory usage, prevent external fragmentation, and make execution possible even when full programs are not in memory. Among with page demand paging and hierarchy page tables, modern system can run big application efficiently, securely and faster. So paging not only improve memory management but also enhance overall system performance. Thank you for listening.